Okay. Give me 1 second and then we'll go for it. Okay. Um, let's go over this. First one, calcium oxide has been proposed as a substance that can be used to heat water quickly for portable heating packs or for cooking. With the calcium oxide reacts as shown by the equation above. Okay. A student wants to design a heating pad that could heat a 150-gram sample of water from 25 degrees Celsius to 60 degrees Celsius. Calculate the amount of heat in joules that the water must absorb for its temperature to change by this amount. Okay, so let me see. Okay, so we want the temperature change to go from 25 to 60 degrees Celsius, right? So this is just Q equals MC delta T, right? So we have Q equals MC delta T, right? The mass, right, that we have is 150 grams. Right, our specific heat, right, specific heat of water is 4.18 joules per gram degree Celsius, right, and our delta T, right, is 25 to 60, so final minus initial, so 60 minus 25 degrees Celsius. 60 minus 25, 35. 35 times 150 times 4.18. I get Q equals 21,945 joules. Right? They wanted in joules, so I would leave it like this. I would change it to scientific notation because of sig figs, but besides that, right? So I would put 2.19 times 10 to the 1, 2, 3, 4 joules. Right? 1 point. Okay. Second part, calculate the minimum mass of calcium oxide that the student would need to use in order to cause this temperature change. Right, so essentially we know that from part one, right, that we had 2.19 times 10 to the fourth joules being released, right? Or this is the amount of energy that would be needed, right? And we have our delta H for a reaction, right? So I would just use that, right? So right, for every 63700 joules of energy, right, I get 1 mole of reaction. Right, again, this is in kilojoules, my answer was in joules. I just want to make sure it's all the same unit, right? And for every 1 mole of reaction, right, I need 1 mole of calcium oxide, right? So this, right, doing 2.19 times 10 to the fourth divided by 63,700 joules, that tells me how many moles of calcium oxide I have, right? And that I could also just continue from here, convert moles to grams. Ugh. Moles to grams. I don't know molar mass of calcium. Let me see. $56. Right, so 56 grams per mole. Right? And if you do that, moles of reaction, joules, joules, moles of calcium oxide, and you're left with grams of calcium oxide, which is 19.3 grams of calcium oxide. Right, so if I burn if I react 19.3 grams of calcium oxide, right, then it's going to release 2.19 times 10 to the fourth amount of joules, which is how much heat needs to be released to go from 25 degrees Celsius to 60 degrees Celsius. Right, so this is 2 points. 1 point for going from joules to moles. Right, so if you started with this value, right, and you use this value, right, to go from joules to moles, that's 1 point, right, and 1 point for the answer for 90.3 grams. So pretty much, if you got 90.3 grams and you showed your work, you get both points. So part A, total 3 points. Okay. Part B. The student hypothesizes that by design of that the design of the heating pad could be changed to enable it to heat 150 grams of water from 25 degrees Celsius to 90 degrees Celsius by using a greater mass of calcium oxide. Use the data in the table below to determine the standard entropy change in joules per mole Kelvin for the reaction. Okay, so they just want to find want us to find delta S, right? So our entropy change, right? And the values they give us entropies, right? So we know it's a sum of our products minus reactants, right? Entropy of our products minus entropy of our reactants. Right? So delta S equals my products, which is CaOH2, 40, minus reactants, which is CaO, 83 plus 70. Right, so delta S equals negative 113 joules per mole Kelvin. And they want it in mole reaction Kelvin, so make sure you use that unit. Right? So part 1 point. Okay, part 2. Is the reaction thermodynamically favorable at 90 degrees Celsius? Justify your answer with a calculation. Assume that both delta S and delta H are constant between 25 and 90 degrees Celsius. Okay. So pretty much, how do we figure out if this is thermodynamically favorable? We have delta S and delta H, right? So we're going to be able to do what? Find delta G, right? Gibbs free energy, right? So we know delta G equals delta H minus T delta S, right? So we found delta H, right, or we know it. We know delta S, we just found it, and then they gave us a temperature, which is what, 90 degrees Celsius, right? So just plug it in, right? So delta H is this guy, negative 63.7 kilojoules. Okay. Um, yeah. Negative 63.7 kilojoules minus T, right? Again, T has to be in kelvins, right? So 273 plus 90. And then what was delta S that we just found? Negative 113 joules per mole Kelvin. 13 joules per mole Kelvin, right? Entropy and our delta H is a different unit right now, right? So I'm gonna change this to joules. Negative 63 700 joules. 273 plus 90 times 113. So negative 22.7 kilojoules. Right, this is delta G, right? What do we know if delta G is negative? It's spontaneous, right? Thermodynamically favorable. Because delta G is equal to negative 22.7 kilojoules, which means delta G is less than 0, right? So yeah. Okay, so this one is also, or not also, is 2 points, right? 1 point for saying yes, thermodynamically favorable. Yes, thermal right? And then 1 point for finding delta G, right, as your calculation, right? Because they want their justification in the form of calculation. So total 2 points. So part B also total of 3 points, right? So 3 points for part A, 3 points for part B. The student learns that the calcium hydroxide produced from the reaction is relatively insoluble and that it dissolves in water according to the equation below. The student prepares a saturated solution of calcium hydroxide and determines that the calcium ion concentration is 0.011 molar. Calculate the value of Ksp for calcium hydroxide. The student wishes to significantly increase the molar solubility of the calcium hydroxide and has access to the following substances: 15 milliliters distilled water, 15 milliliters of 1 molar calcium chloride, 50 milliliters 1 molar potassium hydroxide, 50 milliliters of 1 molar hydrochloric acid. Which substance, when added to the calcium hydroxide mixture, would increase the molar solubility most significantly? Justify your choice based on concepts of chemical equilibrium, such as Le Chatelier's principle. Okay, so they're saying they wanted to increase the molar solubility. So what does that mean? Anything that shifts this reaction to the right is going to increase molar solubility, right? So I have CaOH2, solid. Right? So if I want this to shift to the right, right? Remember, affecting a solid or changing a solid doesn't do anything, so we can't do anything here, right? If I want to shift to the right, I could decrease, right, my amount of calcium ion concentration and decrease my hydroxide ion concentration, right? And right now, we're just trying to find Ksp, right? So we know ooh, why did I skip to D? Anyways, Ksp equals what? Solubility product, right? So it's just concentration of products over reactants, right? Which in this case is Ca2 plus times OH minus squared. Right? You can use a little ice table if you want. I guess that would be the easiest. ICE. Right? Solids and liquids we don't care for, right? Or we don't include, right? What do we know about this? 0, 0 plus x plus 2x. However, we know, or sorry, it should be S because we're doing solubility, although it doesn't really matter, right? However, we know S is what? 0.11, right? But I'm just going to leave it like this, right? So if I plug this into here, that means Ksp equals S times 2s squared, right? So Ksp equals 4s cubed, right? But we know that S is 0. Because it was given to us, 0, 1, 1, right? So Ksp is just equal to 4 times 0.011 cubed. 0.011. And you get 5.32 times 10 to the negative 6. Right? So this is a total of 2 points. 1 point for somehow, right, recognizing that the concentration of OH minus is equal to twice the concentration of calcium 2 plus. Right, so if I did a ice table like this, right, this plus S and this 2 plus S would be that implicit recognition, right? You don't have to like write this out, right? You just have to somehow imply in your calculations that this is true, right? So that is 1 point, and then 1 point for Ksp. So if you got 5.32 times 10 to the negative 6, that's another 1 point. Okay. Okay. Which substance, when added to the calcium hydroxide mixture, would increase the molar solubility most significantly? Justify your choice based on concepts of chemical equilibrium, such as Le Chatelier's principle. Okay, so like I said, right, if I want to increase the solubility of my calcium hydroxide, what do I need to do? I have to make sure that my reaction is shifting to the right. Yeah. So how do I make sure that it shifts to the right? Right? Again, this is a solid, so I can't do anything. I would have to decrease this concentration, right? Given what I have, right, water, I'm not going to do anything, right? I have calcium chloride, I have potassium hydroxide, and I have HCl, right? Which one of these is going to react with either calcium or hydroxide? This guy, right? HCl, right? Because what happens if I add HCl there, right? The H plus is going to do what? React with this, right? And I would get water, right? So if I added HCl, it's going to react with my hydroxide, and my concentration of hydroxide would go down, right? And therefore, Le Chatelier, right, according to Le Chatelier's principle, my reaction, right, equilibrium will shift to the right, right? And when it shifts to the right, right, more of this guy will dissolve, right, increasing the molar solubility. Right? So I would use HCl. Right? Your explanation, anything involving, like I said, um, Le Chatelier, right? So if I use HCl, the H plus will react, right, with OH minus, right? And will react with OH minus, decreasing OH minus concentration, right? So what's going to happen? More CaOH2 must dissolve in order to restore, I don't know, reaction back to equilibrium. Right? Anything about Le Chatelier, right? Something along the lines of that, right? So 2 points. 1 point for picking HCl, 1 point for justification. Okay. Add up the total number of points you got for number 1. I'll be right back. Number 2. Baking soda decomposes upon heating to produce sodium carbonate and 2 gaseous products, as shown by the equation above. A student claims the reaction is an oxidation reduction reaction because the oxidation number of carbon changes. Do you agree with the claim? In your answer, include the oxidation number of carbon in each of the 3 carbon-containing species in the reaction. Do you agree with the claim? Okay, so we have to find oxidation numbers for everything in order to be able to determine if whoever did this correct. Right? There we go. Right, so we know that this is Na plus and HCO3 minus, right? So oxygen is going to be -2, which gives me overall -6. Hydrogen is +1. Right? What is that? +4. Sorry, carbon is +4, right? Right, because +1 +4 -6, right, is -1, right? Here's, we know what? It's CO3 2 minus, right? So again, oxygen is -2 times 3, overall -6. Carbon again has to be +4. Right? CO2, each oxygen is -2, so carbon is +4. Right? So this claim is wrong. Right? Why is it wrong? Oxidation number of carbon in each of these is +4. Right? So 1 point for no or disagreeing with the claim, and then +4. Okay. The student conducts an experiment to determine the composition of a mixture of NaHCO3, molar mass 84 grams per mole. And sodium carbonate. The student places a sample of the mixture into a pre-weighed test tube that is attached to a container that holds a drying agent. The student heats the test tube strongly with the Bunsen burner for 10 minutes, during which time all of the water produced by the reaction is captured by the drying agent. The following table shows the data the student recorded during the experiment. Alright, so calculate the number of moles of baking soda or sodium bicarbonate present in the mixture in the test tube before the reaction was initiated. Okay, so we have massive test tube and mixture before heating, drying agent, and then massive drying agent and water before reaction. Okay, so what do we need to do? Right, or how, let me, Okay. So we have let me see one more time. We have a mixture of those two things. You put it into a test tube that holds a drying agent. They heat the test tube, during which time all the water produced is captured by the drying agent, right? So if you look at our reaction up here, right, you took these two things, right? The only one that we could find, or what we really need to know, is how much water was produced, because that would tell me how much baking soda, right, I would have, right? So how do I know how much water is produced? I would take this guy, right, subtract this guy, right, take your mass of your drying agent, right? How much water did my drying agent capture, right? So 2.303 grams minus 2.134 grams. What is that? 0.169 grams of water. Right? So I need to convert this to moles, right? So 0.169 grams water, 18 grams per mole, right? We need our reaction, hold on. For every 1 mole of water from 2 moles of baking soda, right? 1 mole of water is produced for every 2 moles of sodium bicarbonate decomposed. And this equals 0.0188 moles NaHCO3. So this is 2 points. 1 point for 0.0188 moles of sodium bicarbonate. 1 point for finding mass of water using these values. Right, so this first part is 1 point, and then your answer is 1 point. Okay. Part C, determine the mass percent. So pretty much we need to find our mass of our sodium bicarbonate that we have. Right, so I just found out the moles, right? 0.0188 moles. E4 grams. 60, 80, 84. Yeah. Right, moles, cancel out. 1.58 grams of NaHCO3. right? Now, what is my mass of a mixture? I have my mass of my empty test tube and then mass of test tube and mixture before heating, right? So mass of mixture is going to equal 17.648 grams minus 15.825 grams. 17.648 minus 15.825. So my mass of a mixture is 1.823 grams, right? So my mass percent is going to equal 1.58 over 1.823 times 100%. And I get 86, damn it, I get 86.7%. So this is 2 points too. 1 point for figuring out this guy. 1 point. And then 1 point for your answer. Okay. If the student spills some of the mixture out of the test tube after weighing the test tube and mixture and before heating, how would this error affect the mass percent of sodium bicarbonate calculated in part C? Justify your answer. Okay, so he weighs the test tube, but then he mixes it, right? So what does that mean? The actual amount of, right? It means that this guy, right, is higher than expected, right? How would that affect your mass percent? Remember, mass percent was what? It was our mass of NaHCO3 divided by this guy, your total mixture, right? 17.648, right? So that means the actual value, right, is going to be lower than this guy, right? If this is less, right, how does that affect my mass of NaHCO3? I would have less, right? Because if I have less of my reactant, right, then that means um, I would have less water collected by my drying agent, right? Everything would be smaller than what we actually predicted it would be, right? So my mass percent would be greater, right? So our calculated mass percent would be smaller. anyways, yeah. So your calculated mass percent would be smaller, right? Um, okay. Part E. When a sample of pure sodium carbonate is placed in distilled water, the student observes that the pH of the solution increases significantly. This process is represented by the balanced net ionic equation shown below. Carbonate plus water. Oh, okay. Yeah. Here below. The student prepares 0.1 molar solar carbonate solution and measures the pH of the solution to be 11.65. Calculate hydroxide concentration in the sodium carbonate solution. Okay, so we know pH equals 11.65, right? So we should be fairly easy, right? So pH equals 11.65, right? 11.65 equals negative log of H plus, right? Because that's what pH is, right? So what that means is H plus concentration is equal 10 to the negative 11.65, right? And what do we know? We know that H plus concentration times OH minus concentration equals 1 times 10 to the negative 14, right? So we know OH minus concentration is equal 1 times 10 to the negative 14 divided by 1 times 10 to the negative 11.65, right? Which is 1 times 10 to the negative plus 11.65. What is that? 2.35? Right? That's one way to do it. Another way to do it, you can take pH, right, and find POH, right? 14 minus pH equals POH, right? And then find POH, right? So POH is equal what? 2.35, right? And we know POH is negative log of OH minus equals 2.35. So we know OH minus concentration is 10 to the negative 2.35, right? Either way, same thing. 1 point, right? 1 point for this answer. Obviously, you would do it instead of just leaving it as that, right? You should have gotten 4.5 times 10 to the negative 3 molar. Don't forget units, right? So 1 point. Okay, part 2. Write the expression for Kb. So Kb, right? Is this first, what you want to do is make sure that this is a base reaction, right? So carbonate accepts, right? So it is a base reaction, so we can write Kb, right? If it's an acid dissociation reaction, can you use Kb? No, so make sure what you're doing. So this is concentration of HCO3 minus times OH minus divided by CO3 2 minus. 1 point. Okay, and then they want us to calculate KB. Right, we can do like a little icebox. This is carbonate is 0.13 molar. 0.1 molar, right? Given. Nothing, nothing. Right? Minus x plus x plus x. 0.01 minus x, x. However, in part one, the first part, right, we found the concentration of hydroxide, which was 4.5 times 10 to the negative third, right? So that means x equals 4.5 times 10 to the negative third, right? So that means x times x, 4.5 times 10 to the negative third, right? So squared over 0.1 minus 4.5 times 10 to the negative third. So KB, you should get 2.0 times 10 to the negative 4. Okay, so the student adds some strontium nitrate to the sodium carbonate and observes the formation of a precipitate. Write the balanced net ionic equation for the reaction between strontium nitrate and sodium carbonate that produces the precipitate. Simple, right? I mean, I'll just, for all sakes and purposes, I'll write the equation for you guys. I get NaNO3, which is what? Aqueous. And then strontium carbonate, which is a precipitate. Right. I didn't balance it. There you go. Right, so they want the net ionic equation, right? Remember, what is a net ionic equation? Anytime you have a solution problem like this, and they ask you to write a net ionic equation, they're really just asking how do you make your precipitate, right? So what ions are going to make up my precipitate? I guess strontium ion, right? And then carbonate, right? Aqueous, and that's going to yield SrCO3. Because remember, everything else is going to be spectator ion. Oh, that's linked. Spectator ions, so they're not actually involved in the reaction. So if I did write out my total ion reaction, they would cancel out anyways. Right, so there you go. 1 point. Tetrafluoroboric acid is a strong acid with the formula HBF4. The acid can be prepared by reacting the weak acid H3BO3 with HF according to the reaction or equation above. To prepare a solution of BF4 minus, HF is bubbled into a solution containing 50 grams of H3BO3 in a 1 liter reaction vessel. Calculate the maximum number of moles of BF4 minus that can be produced. Okay, so I have 50.0 grams H3BO3. Right, so convert to moles. This is just basic stoichiometry. Right, 61.83 grams per mole given to us, right, molar mass. And for every 1 mole of H3BO3, I can make 1 mole of BF4 minus. Right, so I get 0.809 moles of BF4 minus. The end. Right. 1 point. Keep on. Okay. Calculate the number of liters of HF measured at 273 Kelvin in 1 atmosphere that will be consumed if all the H3BO3 reacts. Okay. So we had H3BO3 number of liters of HF. Okay, so I'm just going to use moles of BF4 minus because that's what I have. 0.809 moles. Well, yeah, it's the same as H3BO3, right? So for every 1 mole of H3BO3, I'm going to need 4 moles of HF. So that's 3.24 moles of HF. Right, liters is 22.4 liters per mole at STP. Right, 273 Kelvin, 1 atmosphere is STP. Right, so 3.24 moles HF times 22.4 liters per mole. 72.6 liters HF. For whatever, you could just plug it into PV equals nRT, your ideal gas law. Right? Doesn't matter. You should get the same answer. This is a shortcut. Okay. So 2 points for this guy. 1 point is for finding this guy, the correct value of HF, and then 1 point for your answer. Okay, will the pH of the solution increase, decrease, or remain the same during the course of the reaction? Justify your answer. Okay, so let's look at the reaction, right? Obviously, right, as your reaction goes, you're making H3O plus, right? That's one of your products. So what's going to happen to your pH? Your pH is going to decrease, right? 1 point, right? Why does your pH decrease? Because as your reaction proceeds, you're making more and more H3O plus, right? Okay, in another experiment, 0.15 molar BF4 minus solution is prepared by dissolving NaBF4 in distilled water. BF4 minus ions in the solution slowly react with water in the reversible reaction represented below. BF4 minus plus H2O yields BF3, OH minus, and HF. Concentration is monitored over time as shown in the graph below. HF reaches a constant value of 0.0174 molar when the reaction reaches equilibrium. For the forward reaction, the rate law is K BF concentration BF4 minus. Value of the rate constant was experimentally determined to be 9 times 10 to the negative 4 inverse minutes. Calculate the rate of the forward reaction after 600 minutes. Include units with your answer. Okay, so let me see. So rate equals K BF4 minus. After 600 minutes, where was this? 0.0174, right? 600 minutes. I get, and they tell us that this it plateaus at that value, right? So my initial concentration was 0.15 molar. Of my BF, right? And I mean, I'm really just doing an ice table. I guess I'll write it out instead of being lazy. Right? ICE initial is 0.150, right? Nothing, right? And then here plus X, but I know that it's where is it? 0.174, right? So I know X is 0.174, right? So my concentration of BF4 minus at equilibrium is 0.150 minus 0.0174. Right? So that's it. And I just plug it into this equation that I have right here. Right? So rate equals K, which is 9 times 10 to the negative 4 inverse minutes. Right? And then 0.150 minus 0.0174 molar. Right? And I should get rate equals 1.20 times 10 to the negative 4 molarity per minute. So this guy is 3 points. 1 point for calculating this molarity. 1 point for finding 1.2 times 10 to the negative 4. And then 1 point for the unit. Molarity per minute, molarity. Total 3 points. Why is it frozen? Oh, there it is. Don't get rid of this. Oh my god. Okay. Can I not scroll? Okay. Rate law for the reverse reaction is blank law. A student claims that the initial rate of the reverse reaction is equal to 0. Do you agree or disagree with this claim? Justify your answer in terms of the rate law for the reverse reaction. Okay. So, reverse reaction will start at 0. Yes. Agree. Right? Why? For your reverse reaction, right? The initial of your reverse reaction, do you have any products? If you look at your reaction, do I have any products? No, right? So for my reverse reaction, right, I have no reactants. Therefore, my initial rate will be 0, right? The concentration of this guy and this guy initially is 0 because they're products, right? So it will be, yes. So 1 point, if you put agree with the justification. Okay. At equilibrium, the forward and reverse reaction rates are equal. Calculate the value of the rate constant for the reverse reaction. Okay, so we know K KF BF3. We have this, right? And the rate of this guy, right, that we got here was 1.2 times 10 to the negative 4 molarity per minute, right? So we know rate 1.2 times 10 to the negative 4 equals KF. You get that, right? And then what is this? This was, remember, X, right? So this is 0.0174. Right, so KF equals 1.2 times 10 to the negative 4 over 0.174 molar squared. Right, so KF, I get 0.396, and my units. Right, remember for your rate constant, always remember your units. That is very important. So total of 2 points. 1 point for the answer, 1 point for correct substitutions into your rate reaction. Okay, white gold is a common alloy of gold and palladium that is often used in jewelry. The atomic radii of the metals are given in the table above. A particular ring is made from an alloy that is 75 mole percent gold and 25 mole percent palladium. Using the box below, draw a particle level diagram of the solid alloy consisting of 12 atoms with a representative proportion of atom types. Your diagram should clearly indicate whether the alloy is interstitial or substitutional. Use empty circles for gold and shaded circles for palladium. Okay. Uh, 75%, 75 mole percent gold, 25 mole percent palladium. So what is that? 12, 25, 1 out of 4, 12, 3. 3 palladium. And then the rest should be gold. Right? I would draw it. Right? Size doesn't matter. Right? Just something like that. Oh. Right. Atomic radius is almost the same, right? So you don't need to worry about that. One point for this ratio right here. And then 1 point for some sort of array like this, where all of your circles are the same size. Right, so essentially 1 point for shading and 1 point for the rest of the drawing. Right? You just need to have 3 shaded to represent the palladium. Okay, a student hypothesizes that placing the ring in a 1 molar solution of RHNO33 will result in a reaction in which RH metal is deposited on the white gold ring. Based on the information, calculate E for the reactions that may occur between ions in the solution and atoms in the ring, and indicate whether or not the student's hypothesis is correct. Okay, so their theory. RH, right? So we want the reaction to be RH3 plus goes to RH solid, right? And that includes 3 electrons deposited on the white gold ring. So what needs to happen to the white gold? AU right? Will this reaction occur? So this guy, right? E is 0.76. This guy E is negative 1.5, right? So what is that? Negative 0.74 volts, right? Will this battery run? No. Right? Why is it going to work? E cell is negative, meaning that this reaction is not spontaneous. Right? Why? Remember, delta G equals negative NFE. Right? If E is negative, delta G is positive, non-spontaneous. Right? 1 point for finding E. 1 point for saying no and why. Okay, the first ionization energies for sodium and potassium are given in the table above. Sodium metal reacts vigorously with water to form hydrogen gas and a metal hydroxide. Potassium metal reacts vigorously as well, but it bursts into a violet colored flame. Write the electron configuration for a K plus ion. Okay, I don't know. Uh, 19. 1s2, 2s2, 2p6, 3s2, 2, 4, 10, 12, 3p6. I believe. What was the atomic number again? 19. Yeah. You could also have written a shorthand, right? Any 3, 3s2, 3p6. It doesn't matter, right? Okay. Based on principles, oh, remember that K plus. Always, FYI, remember always remove from the highest energy level, right? Okay. Based on principles of atomic structure, explain why the first ionization energy of K is lower than the first ionization energy of Na. Periodic table. NaK. Right, on our periodic table, this is what it looks like. Na is 11, 19K. Right, on our periodic table, you have Na and then K. Remember, any periodic trend can be described by two things. When you go up and down, what do you consider? Up and down a group? Has to do with subshells, right? Right, Coulomb's law. Right, electron shielding. These are all like the keywords that you could use, right? How about when you go left and right? It's really just proton number, right? Which is effective nuclear charge, right? All of your periodic trends are described by this, right? So when we look at sodium and potassium, right? They tell us why is the first energy ionization energy of K lower than the first ionization energy of sodium? K, right? Compared to sodium, K has what? One more subshell, right? It has one more subshell, and based on Coulomb's law, right? Because that valence electron is on a greater subshell, that means it's further away from the nucleus, right? Coulomb's law, distance increases, right? Attraction decreases. Therefore, right, it's easier to remove that one valence electron from K than it is an A, right? I think K, the valence electron is 4s1. This guy is 3s1, right? Because 4s1 is further away from the nucleus, it is easier to remove than 3s1. Right, 1 point. You have to have some sort of justification. Okay, a student hypothesizes that the flame is violet colored because violet light consists of photons that have the energy needed to ionize K atoms. The wavelength of the violet light is measured to be 423 nanometers. Calculate the energy in joules of one photon of violet light with a wavelength of 423 nanometers. Okay, so we know is Planck's constant times frequency. Right? We need to find this guy. Right? Speed of light is wavelength times frequency. So frequency equals wavelength divided by speed of light. Wavelength is 423 nanometers. So 423 times 10 to the negative 9 meters. Whoa. Right. So frequency is speed of light divided by 423 times 10 to the negative 9 meters, right, which is our wavelength. So I should get 7.09 inverse seconds. So I can just plug that into my energy equation, right? Where energy equals Planck's constant, which is 6.626 times 10 to the 33rd per second. And then frequency, which is 7.09 times 10 to the 14. Right, seconds cancel out and left with joules. And I get energy equals 4.7 times 10 to the negative 19 joules. Right, so this is total 1 point. Okay. Is the energy of one photon of the violet light sufficient to cause the ionization of the K atom? Justify. So we just got what? First ionization energy, right, is 4.19 times 10 to the fifth joules per mole. One atom, right? So this is silly. Joules per mole, right? Well, one mole has 6.022 times 10 to the 23rd atoms, right? So this cancels out. And I get 6.96 times 10 to the negative 19 joules per atom. So what that means is to ionize one atom, I need 6.96 times 10 to the negative 19. Right? Do I have enough? No. Right? Part 1, I got 4.7. So answer is no. This value is greater than the energy in one photon of light. Okay. An incomplete Lewis diagram for the propanoic acid molecule is provided in the box below. Complete the diagram showing how the remaining atoms in the molecule are arranged around the carbon atom marked with an asterisk. Your structure should minimize formal charge and include any lone pair of atoms. Okay. Total number of valence electrons is where I'm going to start, right? Remember, so this is 8 plus 5 plus 1 plus 12 plus 1, right? So what is that? 10, 22, 27 valence electrons? Right? 12 plus 6 plus 12 plus 6 plus 12. Oh, that was supposed to be 4. 30. What is this? Right, I have a total of 30 valence electrons, 2, 4, 6, 8, 10, 12, 14, right? So I have C2, H5, COOH, right? This is COOH, you should know, is just carboxylic acid. Right? OOH. Right? This is a Lewis diagram, so I should write it out. Right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. 30 valence electrons, see. And this is really the only way to draw it. I don't know. If you did draw it some other way and it works, it probably wouldn't work. Even if like the numbers add up, because they want you to minimize formal charge. Right? This is the only thing that'll work. 1 point. Identify the hybridization of the carbon, mark with an asterisk, O, OH, right? So 1 group, 2 group, 3 group, right? sp2. 1 point. Okay. Propanoic acid has a lower boiling point than butanoic acid. Identify all the types of intermolecular forces present among the molecules in propanoic acid. H bonds, dipole, dipole, right? H bonds here, dipole, dipole here, right? LDFs. One point. Which of the types of intermolecular forces that you identified in part C1 is most responsible in the boiling points of the two acids? This also has carboxylic acid, right? So it's going to look exactly the same as this, except it'll have one more C. Right? Right. So what is going to account for the difference in the boiling point? It's not H bonds. They both have H bonds. It's not dipole. They both have the same dipole, right? It's going to be LDFs. This one has one more carbon uh, with the hydrogens, right? Greater polarizability because it has more electrons. Therefore, right, that's your LDFs are the reason why you have a difference in boiling points. So 1 point. You don't need to justify it. You just need to list LDF. Okay. A student has 100 liters of 0.4 molar copper 2 sulfate and asked to make 100 milliliters of 0.15 molar copper 2 sulfate for a spectrophotometric experiment. Following laboratory equipment is available for preparing the solution: centigram balance, weighing paper funnel, 10 milliliter beaker, 150 milliliter beer, 50 milliliter graduated cylinder, 100 milliliter volumetric flask, 50 milliliter burette, distilled water. Calculate the volume, of 0.4 molar copper 2 sulfate required for the prep. Okay. This is just M1V1, right? I need to find B2, right? So what do I have? Volume of 0.4 molar, 100 milliliters, 0.0. 15 divided by 0.4, 37.5 milliliters. Okay. It now says briefly describe the. Oh, sorry. That one is worth 1 point. It says briefly describe the essential steps to most accurately prepare the 0.15 molar copper 2 sulfate from the 0.4 molar copper 2 sulfate using the equipment listed below. Above. Okay, so how will we do that? How are we going to measure out 37.5 milliliters of my 0.4 molar copper sulfate solution? I have a burette. I have a graduated cylinder. Which one is better? The burette, right? The burette is going to be better, right? You would, yeah, these are the only two things that you could use to measure it out, right? So step one, use 50 milliliter burette to add 37.5 milliliters of 0.4 molar copper sulfate into 100 volumetric flask. Right. Remember, if we're making 100 milliliters or something, right, the best tool that we can use is a volumetric flask. Right. So we're gonna put it in. Now what I do? Add water. Right. Fill with distilled water. Right. Remember, volumetric flask. Right. It has like a little mark that indicates 100 milliliters. So you're gonna fill it until up to the mark. So 2 points. 1 point for essentially each step. Okay, the student plans to conduct a spectrophotometric analysis to determine the concentration of CO2 plus in a solution. The solution has a small amount of cobalt 2 nitrate present as a contaminant. The student is given the diagram below, which shows the absorbance curves for aqueous solutions of cobalt and copper. Okay, so their sample is contaminated, right? So we look at the absorbance curves. The spectrophotometer available to the student has a wavelength range of 400 nanometers to 700 nanometers. What wavelength should the student use to minimize the interference from the presence of the CO2 plus ions, right? So if you look at the absorbance spectrum, right, we know that our sample is contaminated, but in order to kind of minimize, right, that having much of an effect on our results, what should I do? Right? If the range of the spectrophotometer is 400 to 700, I would get as close to 700 as I can. Right? 700. Because at 700 nanometers, right, cobalt is going to have barely any absorbance. Right? So all that you're measuring should be copper. You should be able to kind of get rid of any cobalt present. Right? So 700 nanometers, 1 point. Can you guys add up your scores? And then the next one is closer for you guys. So get your grades or calculate or add up, and then submit these or comment it. I don't know, whatever you guys normally do. And enjoy the last couple of days of your spring break if you go to Denver. And otherwise, you guys are free to go. Just make sure you guys score it before you leave, so you can give it to. I think it's isn't it always 42? I'm actually not sure. Huh? 46? Yeah. Oh, maybe bio is 42. Let me see. Uh, 10, 10, 10, 30. 1, 2, 3, 4. Yeah, 46. It should be the first three, your long questions are out of 10, everything else is out of 4.